Okay, so we learned about the universal law of gravity. And if you have one object, M1, and another object, M2, and they're separated by a distance r, if you want to calculate how much force of attraction there is between these two masses, we know the formula is Fg equals big G, which is a universal gravitation constant, 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared, times the mass of the first object times the mass of the second object divided by the distance between the two squared. If you plug in values, you should be able to crunch out that formula. We did a few examples like that on Friday. But what we want to be able to do now, folks, is what I personally call the relationship game. And let's say you were told that the force of attraction between these two particular masses was 10 newtons. And then you were told that whatever mass you had over here, you doubled it, and now you had it times 2. And maybe whatever mass was over here, you tripled that mass. It was much more massive. And that mass over there was times 3. So instead of having just a regular mass over here, this mass was doubled, this mass was tripled. We know before the force of attraction was 10 newtons. And the question is, what would the force of attraction be now? So if you look at the formula and you say to yourself, hey, do you see that first mass? That's going to be times 2, twice as great. See that second mass? That's going to be times 3. So if we multiply that whole right-hand side out, it would be 6 times greater. 2 times 3 is 6. So the new force of attraction is going to be 6 times greater. So now, instead of the force being 10 newtons, well, if you double one mass and you triple the other mass, the force of attraction would be 6 times greater, which is 60 newtons. What if you had a mass M1 and you had another mass M2? The distance between them was kept constant, some value r. We know how to calculate that force of attraction. G, M1, M2, all over r squared. Let's say there was a certain force of attraction pulling these two masses together. Let's say this mass was replaced with one was 4 times bigger, and this one was replaced with one that was 6 times bigger. Yes? Well, if this mass is 4 times bigger, this one here is 6 times bigger, and you multiplied all those numbers out, that right-hand side would end up being 4 times 6, 24 times greater than it was before. So whatever Fg was before, now it's going to be 24 times Fg. 24 times greater. You catching on how to play this game? What if you had a mass M1 and another mass M2? Okay. Distance r stayed the same. But what if one of the masses was doubled and the other one stayed the same? Times 1. Well, Fg equals G M1 M2 all over r squared. If one of the masses is times 2, the other mass is times 1, the new force would be twice as great. So whatever the force was before, F sub g, the new force would be 2Fg. So that's the relationship between the masses and the force. Now we got to look at the relationship between the distance and the force. Say we have m1, m2, a certain distance r. Force of attraction, F sub g. Again, we know how to calculate that F sub g. Big G, m1, m2, all over r squared. But let's say we went in and we took these two masses and we moved them farther apart so that this distance now was 2r. They were twice as far apart. So when you go to plug in the values, plugged in here, this would be times 2. But you got to be careful because that r is times 2, but then that r gets squared and it's in the denominator. So what's the deal, Alex? What's the new force going to be? 1/4. It's going to be 1/4 what the original force was. So if you double that distance, the force now would be 1/4 what it used to be. What if the original distance was tripled times 3? So this here was 3 times bigger. What's going to happen to that new force of attraction? If the distance was tripled, what do you think, Tommy? The new force of attraction would be 1/9 of what it used to be. So the relationship between the force and the distance r is called an inverse square relationship. So, for example, if the distance is quadrupled, well, that means that the distance r is going to be multiplied by 4. Well, if you take the 4 and you take its inverse, which is the reciprocal, inverse reciprocal, yes, you have 1/4. If you square that value, you get 1/16. So that tells you that the new force is 1/16 as strong as the original. If the distance was 5 times the original distance, take the reciprocal, 1/5, square it, you get 1/25. The new force would be 1/25 of the original force of attraction. Inverse square law. And then, last but not least, you have to be able to play the mass game and the distance game at the same time. So, say for example, you have M1, M2, they're a distance r apart, and the force of attraction is Fg. If this mass is times 2, this mass is times 2, and the distance is times 2, how would the new force of attraction compare to the original? Don't shout out the answer. Let everyone have a moment to think it through. Okay? Mike in the back, what would that new force be? Yes. Very good. If you look at the formula, Fg equals big G M1 M2 all over r squared. If this one's times 2 and that one's times 2 and the r is times 2, but that r down there gets squared, well, on the top you're going to have 2 times 2, which is 4. On the bottom, denominator, you're going to have 2 squared, which is 4. So, due to the mass, the force would be 4 times greater. Due to the distance, the force would be 4 times smaller. Both factors cancel each other out, and you get the same. Nice job, Mike. So that's the relationship game. Now, a lot of the times, one of the masses is the Earth, and the other mass is like a person. Obviously not drawn to scale here. Earth, person. The whole Earth pulls the person towards the Earth, force due to gravity. The Earth can't pull the person down without the person pulling the whole Earth up with the same exact force. The distance between the center of the Earth and the center of the person, essentially, that's the radius of the Earth, for the most part. This point here is not drawn perfectly. That should be the center of the Earth. So if you're standing on the surface of the Earth, the distance between the center of you and the center of the Earth is essentially 1 Earth radius. How much you weigh? Well, whatever you weigh, that's how much you weigh. Let's say you weigh, 100 pounds. Your F sub G equals 100 pounds. Now, what if you were up here and the distance between the center of you and the center of the Earth was 2r? What's going to happen to your true weight, your actual weight? It's not going to be the same. How much would it be up here, Paul?
It would be 25 pounds.
Yeah, it would be 25 pounds, exactly. If you weighed 100 pounds on the surface of the Earth, you double the distance between the center of the Earth and the center of you. The force of attraction would be quartered, 1/4. So out here, it's going to be 1/4 F sub G. Your weight is quartered. If you went out 3 Earth radii, what happens to your weight up there, Reed? Your weight would be 1/9. Of course, your mass, how much material, how much matter you're made up of, that would stay constant. That doesn't change as you go farther away from the surface of the Earth. but your weight does. It obeys that inverse square rule. I remember hearing an explanation of why gravity gets weaker, and it follows that inverse square rule. And the person explained it by talking about a butter gun that spread butter on toast. They said, imagine if you had a butter gun, and this butter gun shot the butter out, and you put a piece of toast here, and the piece of toast would be sprayed by butter, and it would get so much butter put on the toast, yes? But let's say you were running behind, and you needed to get more toast butter quickly, yes? Well, instead of putting that one slice there, okay, if you move the toast further back, that spray of butter spreads out, yes? And way over here, you could put 4 pieces of toast. Twice as high and twice as deep. Yes? Picture's kind of screwy, but you get the idea, yes? So by doubling the distance between the toast and the butter gun, here it's just 1 R. Now it's 2 R. The same butter gets spread out weaker and weaker. See how it's twice as high, twice as deep? But here's the thing. What's going to happen to the amount of butter that's going to be on the toast out here? How much less? It's going to be 1/4 what it used to be, yes? And if you put the toast way out here, it would be 3 times as high, 3 times as deep. The thickness of the butter would be 1/9 of what it used to be. So just as the butter gets thinner and thinner, as you get farther and farther away from a planet, the gravity gets weaker and weaker. One last thing, the same relationship holds with light. If you're near a flashlight, the flashlight is so bright here, well, if you double the distance and you go out here, guess what's going to happen to the brightness of the light?
No, it's bright.
Dimmer. How much dimmer?
1/4.
1/4 of what it used to be. All right, take a break, come on back.